Starting recording officially. So, hello. Happy Thursday. Yeah, happy garbage day in Solon, as I say it wrong every time. So those of you who are celebrating there, not in my neighborhood. I wanted to make sure you all knew that your chance to try out the online homework system is up and ready for you. So that is, let's see, I'd like you to do it by Monday night if you can. That way I can catch any typos in my database. If I accidentally put extra spaces in your name or something and you can't log in, I'd like to know about that sooner rather than later. One of the questions on there I wanted to draw your attention to is how many regular days of class are we scheduled not to have? Usually the answer in a semester is 0 or 1, but this year it's 2. I'm giving you an extra fall break in October. Did you know that? Yeah, right here. So this week I am traveling to a conference in Ithaca, New York, which takes a very difficult time to get there, by way of Omaha, where I can take my son to my parents' house to be babysat while we are conferencing. So that whole week, you do not have class or office hours from me. So a little bit of a mid-fall break. And then we get the official fall break according to the university, which the rest of us call Thanksgiving. So these don't count as days missed because they're not part of the university calendar, but this week does. If we are behind relative to where I'd like to be in the syllabus, I may record some videos for you to watch while I'm away to kind of catch up and finish that unit. But if not, then you can just have a week off. We all need a break sometimes, right? Especially by that point in the semester. Get your Halloween costumes ready, you know, that kind of thing. You can put it to good use. Otherwise, after homework 0, we have a couple of formative assessments, and your first homework is not due till the end of September. So, not a whole lot of workload just yet. Is it SMEP? Yes, it is. The Society of Multivariate Experimental Psychology is the conference that I'm going to. We hosted it here in Iowa last year. I'm the past president, so after this, I am off their board of whatever you call it, board of trustees. So, hooray for me, less responsibility. Anywho, let's see what we were talking about last time. We were talking about an example, not this one. Hang on, this one, that one. This look familiar? Getting used to the idea of models for the variance and how that interfaces with testing the fixed effects that we care about. So just to refresh our memory, we have a very limited example to start off with. This is example 3A, where I have a design with, let me get I know what slide I wanted. I had it open. Here it is. Pre-test versus post-test as the longitudinal component, because 2 occasions is the bare minimum to have something be longitudinal and not cross-sectional, which means 1 occasion per person. And we have 2 groups, a control group and a treatment group. You can pretend they're randomly assigned because this is fake data and I know what's going to happen. So the cell means, as they are called, for each unique combination of occasion and group are here, along with their standard errors. The numbers in the boxes are the model parameters that we're going to have come back to us. The question is whether or not these differences indicated by the numbers in the boxes are significant. And what we will see today is the exciting conclusion to the story that the answer is it depends on what model you use. So first thing we had to do was restructure the data. So if you have data that are stored in a traditional format known as wide, or I call it multivariate sometimes, with 1 row per person, that needs to be restructured, or reshape is often what the command is called in software, from wide to long. So we're taking each row of a person's data and transposing it 1 by 1. And this is the gesture that I do to go with that. See, the Zoomers, you get this live. The YouTubers, not so much. This extra $1 tuition right there for this gesture. Every software package has a built-in thing to do this, even SPSS. So never, ever try to do this manually. Once the transposition happens, then you should have 1 row per occasion per person. And the rule is all rows that are complete get included in your model. All rows that are incomplete do not. So if somebody had a pre-test occasion but not a post-test, we would still use the pre-test occasion that they have, we just can't use their post-test. That's because we are changing the method of estimation from ordinary least squares, which requires complete data, to some kind of maximum likelihood, which does not. more details on that forthcoming. Question from the Zoomers. Why does it have to be transformed from wide to long? Does the software just work better when it's that way? Standard off-the-shelf multi-level modeling software will insist that you have it this way because that software is looking for one column as the outcome. So you have to combine all of your different outcomes into one column somehow in order to feed that into the software. That is for multi-level modeling approaches to longitudinal data specifically. If you are trying to fit the exact same models using structural equation modeling software instead, which I will show you a couple examples of at the end of Unit 5, and then that will show up much more in the advanced class. In SEM, you would use the original version of the data, and you would have a box for outcome 1 and a box for outcome 2. In roll your own software, as my husband calls it, things like Stan or JAGS or stuff like that, you can have whatever data structure you want, right? It's up to you and how you program your algorithm. So I'm referring to this as needed by conventional approaches for multi-level modeling, which is what I'm mainly here to show you this semester. Does that answer the question? Okay, cool. All right, so once we're done changing the data set, we have a column for occasion, a column for group, and a column for outcome. So we walked through empty models. Remember what that term means as a definition? No predictors. In regression, I start at an empty model. That's what I'm going to be doing at 2 o'clock today for pedagogical purposes only. In longitudinal models, it is always the first thing you do because an empty model tells you if you even have longitudinal data in the first place. How much of your variation is because of constant person mean differences over time that were going to be there anyway versus how much of it is because you added these additional repeated measures to see how people change over time. So we had first as our baseline, the simplest possible model, call it E only because the model for the variance is what we're focusing on and that has only this E term. This assumes that people are independent and occasions are independent. So independent is what the structure is known as in Stata mixed. And I'm using GLS within the LME package within R today. Correlation equals null does the same thing. So no correlation between occasions from the same person. We know this model is not a good idea. It's a reference point to see how things change relative to fitting a model that does allow a correlation. So that was the next thing that we did. Another way to say that is this tiny little matrix right here that no other software would print for me except R, or SAS from this model, excuse me. This is what the model says the variance covariance matrix looks like for the occasions over time, where this would be pre-test and post-test. We're saying that the total variation across people at pre-test is 40, and it's 40 across people at post-test too. And this blank cell here means zero covariance or zero correlation. So this is the same thing that you would see in a standard regression model. Like if you had a giant matrix for all the people in your sample, this is what it would look like. Constant variance on the diagonal and then blankness everywhere else. Within our longitudinal data, you can think of this as like one little pocket of the giant matrix. The term for that is block diagonal, where you would have like all the people and all the occasions. So this would be like time 1, time 2 for person 1, time 1, time 2 for person 2, time 1, time 2 for person 3. And this is the time 1, time 2 part for everybody. So it'd be like doot, 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 doot. The more technical version of this is coming soon, but this is foreshadowing. And again, doot, 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 if you want to take notes on that. So if we add a correlation, then the key word that changes to in terms of what the residuals are supposed to be in Stata is exchangeable. That is synonymous with compound symmetry if you are using SAS, and that means that we are adding this extra term here to our model for the variance. And what is that thing called? Looking for a 2-word phrase, first word starts with an R. Second word starts with an I. We'll play hangman if that's what it takes. That's it, random intercept. Each U is for you. That's why it gets an I. Each of you gets your own random intercept that operates through all of the occasions that you have. In this model, we don't care what U0 is for each person. It doesn't matter. We could predict it after the fact if we wanted to, but we don't need to. What we care about is how much variability there is in these U variables across people. That's what we care about. Just like we care about how much E variability there is across people and occasions at level 1. So yes, thank you Zoomers, random intercept for a win. So U plus E is how I'm abbreviating that in these titles, just to remind you that we have two different variances we're paying attention to now. One that is between persons and one that is within persons. Which is which? Is U between or within? Between. Is U level 1 or level 2? 2. Is U inter or intra? Inter. So that means E is level 1, within, intra. Micro. Stacking all the words back together again. I told you we're going to keep doing this every class. Commit it to memory. So in this model, we have a different prediction. The way that the parameters are expressed differs across software packages. In Stata, what you get back is the total variation across persons and occasions, and then the part that is due to persons as cov E. In SAS, for instance, you get the residual variation specifically, not the total, and then the cov thing separately. So what it looks like when you put it into a matrix like this, let me zoom it in. That's about as zoomy as I can get. Now we still have our diagonal of about 40-ish. It was like 40.3 before. Now it's like 40.5. It's not going to be exactly the same unless you limit estimation in a particular way, but that's not really important. The point of the story is that we're saying there's the same amount of variability at pre-test at post-test. That's what we said before. But the reason to add the U is this part right here. The point of splitting up the variance into a between pile and a within pile is not to change the overall amount. It's to change the model to allow a dependency, to allow some kind of relationship between the outcomes from the same person. So this matrix is being partitioned into how much is due to U and then how much is left over due to E. U is everywhere in this matrix. E is added to just the diagonal. So that is, I can show this a little more concretely. Had a slide on that, yeah. So here's an example with 3 occasions. Like this is the structure that is being built. E variance plus U0 variance on the diagonal, the same the whole way across all the occasions, and then nothing but U variance on the off diagonals. So this is saying, yes, there is a correlation between occasions from the same person, and the extent of that, when expressed as a covariance, is person mean differences. Because some people are higher than others, that induces a correlation in their residual specifically. And once we allow for that, there's no other reason why the occasion should be related. That's a testable hypothesis. And if we convert this variance-covariance matrix, as it is called, variance is on the diagonal, covariance is on the off diagonal, to a correlation matrix, then the correlation between occasions shows up as our interclass correlation. So in our example, that intraclass correlation computed right here, U0 variance in the numerator over U0 variance plus residual variance in the denominator, or between over total for short, gives me a correlation of 0.3. So give me 2 different definitions as to what that means. Who's feeling brave today? In Zoomers, I'm watching the chat, I promise. You can play along. Kendall, you're not feeling brave? It's like, nah. We were just talking earlier about how it's Thursday and we're all really tired because we've been in school for like 2 whole weeks. My son included. Like, it took me extra time to wake him up this morning. He was dead to the world. So, 2 definitions of ICCs. I don't want to cold call on people, but I will cold call on people if I got to. You're feeling brave?
Is it the ratio of variance from between person variation to the total?
Yes, it is. So put that number in a sentence that says that.
So the interclass correlation tells us the ratio of variance that's explained by interperson variation to the total amount of variation.
Yes, so 30% is because people are different from each other on average out of the total. From the Zoomers, 30% of the variance can be attributed to between-person variation. So in the clustered class, I used to say between cluster, and that was the end. I got to be more specific in this class. It's not just between-person variation, it's between-person variation in their means specifically. Between-person mean variation is captured with a random intercept that introduces a constant source of correlation or covariance of occasions from the same person. The reason I'm being more specific is because we're going to have not just mean differences, but also differences in change, right? People change differently. That's another kind of between-person variation that's going to show up. So I got to be more specific that this is one kind. Other definition given in the chat window: for the same person, the correlation of occasions is 0.3. Yeah, the correlation between time 1 and time 2 is 0.3. I can also say it that way. And I know that's weird to think about it as like the within-person correlation when random intercept variance is in the numerator, but think of it this way. Like if I had a correlation of 0.9, like I would be really certain I could predict your other occasions from that, right? I just need to know one and I can make a pretty good guess as to what the others are. Like there's a lot of constancy running through that. So that means most of the variation is between persons, not across their occasions, because the occasions are all really highly related. Whereas if I had an ICC of 0.1, then I couldn't do a decent job predicting your other occasions given only one. There's as much variability within a person as there is between people. There's a lot more within. And this number ranges from 0 to 1. If it's 0, that's okay. If it's 1, that's not okay. If it's 1, what does that mean in terms of doing a longitudinal analysis? Looking for a 2-word phrase, first word starts with a G. Game over. I would also accept correct wah wah. Any other synonyms you'd like to add to that list? Stick a fork in it, you're done. Take your ball and go home is another one I will also say. We talked about expressions we use in the other class, so I'm introducing you to some of my favorites. Anyone want to add? Screwed up. Well, it could happen for reasons that you have no control over, right? Like in this particular example, they answered the same thing every time. Like the construct being measured just didn't change. We would call that a time invariant variable. So like if you ask somebody, how many years of education do you have, and you're asking an adult sample, most of them are going to say the same answer all the time unless they're actively in school. Another expression, let's see, no. Did I say that correctly? I would also accept yeah, no. Yeah, no means I understood your question and the answer is no. All right, anywho, so yes, 30% of our variance is because some kids in this fake data set are better at this outcome than others on average. 0.3 is the correlation between time 1 and time 2. That's what we know so far. We have not talked about likelihood ratio tests, but that is showing up later today. There is a significance test for whether or not this 0.3 is different than 0, and it is. I'll just tell you that right now. In R, the same model, adding U plus E, is this thing right here, CORD-COMP-SIM, which stands for Correlation Compound Symmetry. And it does want to know, via the parentheses behind it, how the rows are grouped by person. So that's your level 2 ID variable that would go there. GLS gives you that correlation as part of its output, but it doesn't give you anything else. You have to dig for it. So I added a command, get varcove, to show the model implied R matrix. So there's my 40s on the diagonal. Not the beverage, the variance. And 12 for the off diagonal. That's the amount of variability due to the random intercept. That's also the covariance in this model. And then here's my correlation version of 0.3 in the next one, core matrix, out of a piece of the output buried inside the results of that. Question, so if the ICC were something like 0.9, that would mean that the variation between people is high or not necessarily? It would mean high. It means that 10% of your data are longitudinal, essentially, have longitudinal information, and 90% are cross-sectional. In the world that I live in the world of cognitive aging and psychological data, ICCs tend to be pretty high. There's a lot of constancy to a person. In younger children, less so, because younger children are more homogeneous, it seems like, at least in the world that I've seen before. In clustered data, a high correlation would be something like 0.1 or 0.15. You see a lot smaller ICCs in how people are nested within groups relative to occasions from the same person. Okay. Excellent. Other questions or thoughts? Okay, so then by the way, I believe I fixed this, the ones and zeros that were wrong. Whenever I find typos in my handout, I will fix it after class and repost it. That way you can always have the correct version to refer back to if need be. For those of you who are teaching or preparing course materials, that is one of my pro tips. Always fix your typos right away, because 2 years will go by and you will find them again. Like, if you don't do it, they're going to disappear from your memory. Questions. So between here is between times, not between people, because we are not in cluster land. Between is person, so level 2 is between, level 1 is within, but level 1 is time and level 2 is person. So between person is level 2. Does that help? Okay. All right. Do we want to talk through any of this stuff again? Or are you feeling okay with predicted outcomes and simple slopes and stuff like that? Yes, re-go over is 1 vote. I'm seeing a lot of frowns, and so I'm going to translate that as to re-go over as well. So for those of you who are new to the program, re-go over means present as if we've never heard it before, as opposed to review, which is like assume that there's some prior knowledge. Okay, so I'm assuming that you've seen stuff like this before, like building a predicted value by plugging in the values of the predictors that you want the prediction for. The hat over the Y, by the way, that little carrot looking thingy, that's to denote that we're talking about the predicted outcome for anybody with this profile, not any individual. So it's a conditional group mean, in this case, for the control group at pretest. Everybody who falls under that condition would have the same predicted outcome. It's the E at the end that would differentiate an individual outcome from what's predicted. So Y hat just means the model for the means fixed effects part. So in terms of finding simple slopes within interaction terms, the rule is go into your equation, find all the terms that have the slope you're interested in, and bring them with you. So for the first one, for instance, actually let's do this one. We'll do time slope for treatment group. Time slope is what I want. So right away that tells me I don't need beta 0 because it doesn't have time attached to it. I do need beta 1 because it does have time. I don't need beta 2, even though what I want is the time slope for the treatment group, because beta 2 does not have time attached to it. I do need the interaction term, which is how I'm going to get the time slope specifically for the treatment group. So once you've isolated the 2 things that you need, which are right here, maybe more than 2 in complex models, then you factor out, suck out of both places, the variable that the slope is for, and what's left is what goes into the programming statements to be able to compute a predicted slope for any level of the moderating variable. So the time slope for someone in the treatment group is built from this little combination right here, beta 1 for the main effective time, plus the interaction term for how the effective time differs between groups, plugging in which group you want the time slope for. So this is why we interpret beta 1 specifically as the effective time when group, the moderator, is 0, because that's the only combination in which this combination would reduce to just beta 1. Okay, how is that? So if you come down to the syntax for that same command, time slope for the treatment group, we'll do that one in particular. In Stata, it would be right here, this one. I'm using the command post estimation command. I knew that one. LinCom, I believe, stands for linear combination. And I am asking it for 1 beta 1. So when you type the name of the variable in these statements, what you are asking for is its fixed slope in the model. That is what the words mean. And then the question is, do I need any multipliers of that fixed slope? The equation I'm trying to build is beta 1 plus beta 3 times 1. So I'm putting in the times 1 here to emphasize that I need one of those. Here's my interaction term. So in Stata, interactions are hashtags or pound signs, whichever you prefer. And I need one of those because I'm asking for the time slope when treatment is 1. If I wanted the time slope when treatment is some other value, I would plug that in instead, such as when I'm talking about the control group. Why do we need the small after LinCom? Oh, because Stata is annoying. So here's why. The default in mixed is to use walled tests without any denominator degrees of freedom, meaning z's instead of t's, chi-squares instead of f. That assumes infinity for your sample size. So in small samples, that's going to be wrong to some extent. So that is what this extra piece in the modeling statement says. No, I'd like you to use degrees of freedom. In particular, I'd like this kind. Residual is what is used in traditional linear regression because that's what this model is. It doesn't have u in it yet. And then I'd like the degrees of freedom to be shown with the p-values in the output table. So that's just a display thing. So you would think that because all of these post-estimation commands understand that this is the model that I'm asking for stuff from, that they would also be like, you want degrees of freedom, right? Because you asked for them up here? No, they don't assume that. So every single thing you write, you have to do comma small, which means the small sample size correction that I already asked for up here. I know, annoying. But that's why. Did that help? Okay, cool. All right. The same concept in R, buried down here, so I'm skipping over some stuff for right now, is implemented. There's a couple different packages that do it. I tend to use this one because it works for a lot of different functions and procedures. I'm using something called GLHT, General Linear Hypothesis Test, I believe. And what this is, these are the multipliers that go with your fixed effects in the order in which they appear. So here's my equation, and this is the order in which it appears in the output. So beta 1 is in the second spot, beta 3 is in the last spot. That means that if I want to ask for the time slope for the treatment group, which is right here, I don't need any beta zeros, so that's a 0. I do need 1 beta 1. I don't need any beta 2s. I do need 1 beta 3. So these numbers inside this set of parentheses here directly match the numbers that show up in like the Stata commands when I write it out, where is it, time slope for treatment, like right here, just leaving out the ones that are 0, or they directly match like this little kernel right here. So it's a trick to figure it out, but the key thing to remember is that in the post-estimation commands, when you type a variable name, you're referring to its beta. When you give a number, you're saying how many of them you want as a multiplier. And if you're like, what the hell is all of this? I've never heard this before, that would be a good thing to review on your own while I'm at my conference in October, perhaps, because everything in longitudinal is quickly going to become some kind of interaction term. Like if you want to know why people change differently, that is an interaction with time for everything. Okay, how are we doing? Thumb check. Remember, you get the whole continuum from terrible, so-so, to awesome. Zoomers, we got a couple thumbs. All right, folks are quiet today. Please. Nope. Nope. You would think. But no, no. This is the opposite of transparent. The only thing that saves this is the capacity to write these labels next to it to figure out what the hell you're doing. What the first one is, let me go back up to the R code here. So zooming in so we can see that a little bit better. Here's my model. The 1 is the beta 0. The first one is beta 0. The second one is beta 1. The third one is beta 2, and the last one is beta 3. It only shows up once, even though it's doing two things at the same time. And this is why when I write R code, I always stick the 1 in to remind myself that the first thing is the intercept, because I'm prone to do the exact same thing and say, well, this is my first slope, this is my second slope. Nope, can't forget the intercept. And so you'll note in the list of coefficients here, the first 4 are predicted outcomes. So the intercept is turned on in every single one of them because the intercept applies to everybody. In the matrix representation of a linear model, the intercept variable that fixed intercept would multiply is the column of 1s, just like this. But then the other variables are selectively turned on and off based on which group, whether you want the reference group as the 0 or the alternative group as the 1. And for continuous variables, these can be, 5, 6, 12, whatever they need to be to get the prediction for that kind of level of your covariate. But once you get down into the simple slopes, and I wrote the interaction term out just so everything's in one place, none of these have a 1 in the intercept first spot. Because all of these are asking for some kind of slope, and the intercept has nothing to do with that. Okay.
So I have a question regarding the degrees of freedom. You mentioned denominator degrees of freedom. So
Yep.
what's the difference between? I can see that numerator degrees of freedom, denominator degrees of freedom 48. So where's 48 from?
It is number of people minus number of fixed effects at that level. Degrees of freedom is a whole thing in these models because there's not one answer as to what they should be, particularly for unbalanced data. So there are multiple methods of computing degrees of freedom, and some of them work better in smaller samples than others. The one that you'll see me highlight in this class is something called Satterthwaite. That's a person's name from like the 1940s. It is based on the same logic as a dependent samples t-test with unequal variances and unequal group sizes. Like that was where it came from, I think. And it essentially tries to figure out how much information is at each level and allocate degrees of freedom accordingly, according to sample size and variance at each level. So this is a very straightforward case because we only have 2 observations per person and everybody has the same. So when you get to, actually in this model, the residual degrees of freedom, I'm basing it off of what SAS does it because it understands that the data are nested even though we didn't put a correlation in. When we get to the next one, so adding the U plus E, then I'm still using residual, it looks like. Does it have outcome? I didn't show the output. If you look on the Stata output online, like for the other examples that we're going to see, you'll see decimal values for degrees of freedom and stuff, like it's being estimated. So it's a sort of a weird thing. We haven't touched on that too much, and I don't spend a lot of time on it. I have some material about it towards the middle of chapter 5. But there's more than one way to do it. The differences stop mattering at some point once your sample is large enough. And that's where like the world of Stata is sort of expecting you to be, I think, that it's not relevant.
Thank you.
Sure. And this is only a thing, by the way, for multi-level models that have a residual that is normal. Any generalized models, there's no degrees of freedom, like in most packages. They don't even bother. It's just chi-squares and z's. Okay. The conditional model then. So we looked at the results last time, and we earned ourselves a wah-wah. So this one is the model that doesn't have a random intercept, so a point of comparison. This is a standard straight-up linear regression model, ignoring the fact that I have 2 occasions from the same person. Do you want to go over the coefficients again, or are we feeling okay with those? No one wants to vote. All right, we'll go over them then. That should be my default. I just don't want to bore you, that's all. But I also recognize that not everything is understood perfectly the first time, particularly in the second week of school when we're all tired already. All right, intercept. Given my coding scheme, this is for pretest control group. I centered my variables ahead of time so that the intercept will mean something, because it is always the expected outcome when your predictors are 0. That is what it meant in regression. That is what it's going to mean to us too. Main effective time, as they would call it, given the interaction term, is actually a simple main effect or a conditional main effect, meaning that it only applies to the 0 value of the moderator. So this is the effective time specifically when treatment is 0, which is my control group. In those kids, they grew 5.8 between pre-test and post-test, and that is significant. So yay them. Treatment, likewise, is also a conditional main effect or simple slope. Given the interaction term, it is specifically when time is 0, which is pre-test in my coding scheme. So treatment says that the treatment group is 1.68 higher than the control group at pre-test, which is not significant, and that is a good thing because that means random assignment worked in my fake data. I'd be really sad if it didn't. It's like, you had one job. Then the interaction term. So the key to getting these interpreted correctly is not to talk about what happens to y. This is not what happens when it's both pre-test and or both post-test and treatment. Like, that explanation falls apart very quickly when you start to get into moderation with continuous variables. Instead, the role of an interaction is to take each of its main effect slopes and do one of 4 things to it. Make it more positive, more negative, or less negative. Those are the only possibilities. Sometimes you get into weirdness where something is becoming less negative and then it heads over into positive, but it's one way on the number line. So in this case, given that everything in this story is positive, there's only one possibility. I would say that either the change from pre-test to post-test is more positive, greater by 2 in the treatment group, or I could say the treatment group benefit at pre-test is larger at post-test by 2. Beta 3 does 2 different things at the same time. It tells you how this time slope differs across treatment groups. It tells you how the treatment group difference varies over time. Either one is equally correct. So which is the predictor and which is the moderator is entirely a substantive decision. It's usually based on your research questions and how people tend to think about things. In this context, I'd say it's far more common to go this way and talk about change and then how change differs as a function of person characteristics. That's how people would typically approach this problem. But this interaction term is not significant, so we would conclude that no, even though it looks like the treatment group improved more over time by 2, that's not a significant difference. However, this model says that there's no correlation between occasions from the same persons, that people are independent. Or people are independent, occasions are independent. Pro tip, Nikki says, the homeworks will often ask you for both interpretations. Yeah, that is true. I do tend to go both ways in the story problems, but there's not going to be as much of that until the end of this class, though, because we're going to be spending the bulk of it on change over time without moderation, and that will be the very last unit. But in interpreting, say, quadratic slopes, those are interaction terms, so the same logic will apply there. So what happens if we fit the right model? So this was funny. I wanted to show you this. I wanted to get a joint test of the model R-square like you would have in regression. Like, how much variance does this model account for with these 3 things? That's a standard thing you'd want to know. So I did that in GLHT. There is a different way of asking for it, where you write out, like, what if this slope were 0 and that slope were 0 and that slope were 0? And then it gives you a hypothesis test with 3 degrees of freedom, zeroing out all of them simultaneously and showing how your model would change. And normally, that would be given as an F, with 3 degrees of freedom in the numerator, whatever in the denominator. So I did that, and I was like, I'd like an F test, please. And it's like, no. In angry red font. I know, I copied the color so that you could see how angry this message was. It's all indignant. DF residual is not available for model. A chi-square test is performed instead of the requested F test, and this is what I got. And I was like, come on, dude. Everyone else on Earth would have no problem with this. So chi-square of 50 on 3 degrees of freedom, if I take 50 and divide by 3, I get my F. The only difference is the p-value that will go with it. F uses denominator degrees of freedom as part of its reference distributions, and chi-square does not. So I was like, really? I can't have an F? And lo and behold, I went and started digging through the objects, and it computed it. It just wouldn't print it for me. It's like, no, I'm the boss of you. Are you kidding me? So I was like, fine, I'm going to print it. Watch. F is 16, which is 50 divided by 3. Here's my numerator degrees of freedom, same as this, and here's the denominator degrees of freedom that I told it. So my p-value is still 0 to several decimal places, same conclusion. We're not going to do R square yet because that's a whole thing, but you could compute an R square out of this as well if you wanted to. So let's fix it. Here are the simple slope thingies that I showed you before, all the predictions and whatnot. The last one is my interaction that's non-significant. So if we say, hey, let's let the occasions be correlated, because they probably are. How much were they before? Do you remember what number the correlation was?
0.3.
0.3. Okay, do you think it's going to be the same? Probably not. In the empty model, we were asking how correlated all of time 1 was with all of time 2. But now we have the leftover parts that are not predicted by group treatment and their interaction. So it's not the same thing that's being correlated. So we can't reasonably expect the same answer. Job security, yes indeed. So I put the residuals back to exchangeable in Stata. Everything else is exactly the same. Here's all the linear combinations. Those are all exactly the same. Literally the only thing that changed is this word right here. And here's the same thing in R. Only thing that changed is this part, the core comp sim thing, and then all the attachments that go with it. First thing we see, our new row, which I'm going to bold here, is correlation of 0.84. Yeah, that's a big difference. The leftover parts of occasion 1 and occasion 2 are correlated 0.84. So that implies a lot of dependency left over. A stronger correlation among the residuals after the model has its say than before. A correlation of 0.84 is decidedly significant. So there's a couple weird things that show up in this result, reasons for which we will uncover throughout the semester. One is that the total variance is now down from 40 to 27. That's fine. But the covariance used to be 12 and now it's 22. That is because of how random intercept variance is calculated. They are yoked together. Anytime that you explain level 1, the level 2 variance has to go up, and it almost doubled in this case. There's a reason for that. But the take-home message is that there looks like to be a lot stronger relationship between the residuals of time 1 and time 2 than there was of the originals of time 1 and time 2. The residuals versus the originals. Now, what does this do to the things we care about? That's the question. R still didn't want to give me the F. I'm like, watch, it's 90 this time. Before it was 16. So the exact same model had an F value of 16 before, now it's 90. It's a huge difference. Here's all the linear combinations, Those have not changed one bit. We're still asking for the same pieces of information. We're just doing it with a different error term. Let me zoom back out so you can see the results. Now the time by group interaction. Did I put it up here somewhere? Yes, I did. This is easier. Let's zoom up here. So, intercept, still 49. Time effect, still significant, about 5. Treatment group effect, still not significant. Oh, and lo and behold though, interaction term, now significant. P-value was 0.3 before, and now it's 0.01. So let's dive in and compare the two solutions. I put them next to each other so that we could do that. I got to zoom back out though, but it's hopefully in front of you in some way, shape, or form. I want you to play Where's Waldo with me. Do you know that game? Where's Waldo is a picture game, like for children, where they have these very, very, very compact, like complex pictures, and you have to find a character named Waldo who's wearing a red and white striped shirt. So this is the stats version of that. Find the difference. So here are the results from the model that's E only, saying that occasions are independent on the left. The model that we just looked at, saying, no, I need a random intercept and a correlation of 0.8 that it implies on the right. Now let's go through column by column. What do you think about the values of the slope estimates themselves? Same or different? Standard errors. Somewhat different. So the intercept is the same across the two. The treatment effect is the same across the two. What has changed is the standard error for time, which is much smaller in the within-person version of the model, as well as the standard error for treatment by time, also much smaller. The reason has to do with what error is and what is eligible to be error. In the model on the left, with E only, there's no covariance across occasions from the same person. There's only error in one pile. Everything is E. So all of these are tested using the same residual variance in the formation of the standard error. That's what the numerator is. Whereas on the right, we're making a distinction of kinds of error. 80%, 84% of the error that remains is between persons. That should not matter at all for change over time. Differences between people have nothing to do with why one person changes relative to themselves. Whether it's occasion 1 or occasion 2 as a predictor variable cannot explain why you and I are different. Logically, it can't. And the same thing applies to the interaction term. This is treated as a within subjects effect. When I first learned analysis of variance as an undergraduate, and then I saw it again in graduate school, of course, the way that it was explained to me is that the difference between subjects ANOVA and within subjects ANOVA is that within kicks out the part that's due to constant individual differences because each person is their own control, and therefore all of your tests are stronger for within effects. The kicking out part, I just sort of accepted at face value. I never asked where it went. It's still here. It's you. That's the part that differentiates the two. So by allowing person mean differences as a separate variance component, it logically applies to everything that has to do with people predictors in the model. E logically applies to everything that has to do with time predictors in the model, but also person. So level 2 things have error from 2 and 1, but level 1 things only have error from 1. So there's 80% less error, 84% less error, essentially contributing to the standard errors for these two terms across models. Now, fortunately, which one we would report and believe in does not have to be a subjective decision, right? Because you could see that going awry. Like, well, I would like my interaction term to be significant, so let's go with the one on the right, right? That's not good. What that boils down to, though, which model should be preferred, is which one better reproduces the original data. Whether or not that correlation of 0.84 needs to be there. That's a hypothesis test. It does. I'll just tell you that. As you might expect, a correlation of 0.8 is not 0. So because the model gets taller, the log likelihood is higher for the data given the model parameters after adding that, we would want to keep it. Okay. Any that you want to hear again or hear differently? Take-home message: if you ignore nesting, your p-values are wrong. Sometimes they're wrong in a good way, sometimes they're wrong in a bad way. Because each one needs to understand which source of error variance is relevant for quantifying its inconsistency. If it's a person thing, it's all the variance at 2 and 1. If it's a time thing, it's just the variance at 1. How's that? And all of this is chapter 3, by the way. So, yes?
How do we talk about this? Because I'm used to thinking of fixed, like, intercepts and slopes and saying you control for variance from this predictor.
Mm-hmm.
But when we're talking about adding a random, or we're controlling for a random intercept, we don't use the word control. What
Right.
language would you use?
Okay, so the question I'll repeat for the recording is, how do I talk about this? Because you're talking about adding random things, not fixed things. And fixed things explain variance. They make it go away. You're controlling for this and looking at what's left. We're not doing that. We're figuring out how much variance we have in the first place of each kind. So an analogy I can give you out of real life is I used to watch many years ago Susie Orman. She's a financial guru. She had her own television show. People would call in and ask for advice. And the thing about it is that the people who called in were usually in dire straits. You know, they'd had lots and lots of credit card debt and lots of loans, and they had lots of problems. And I usually felt pretty good about myself because I wasn't as poor as them. And I'm sitting there doing my nails and living my little grad school life. And she would counsel people who had become so overwhelmed with their financial problems, they didn't even know what they owed. So step one was, all right, you know those bills you've been throwing and hiding? Like, you got to start opening them. Figure out how much you owe to whom in the first place, and then you can start making a payment plan where you focus on the loans that are the highest interest first, and then you work your way down to the lower interest things or the things that are, you know, more important or whatever. Like, this process of figuring out what kind of variance we have is like, open your bills. Like, what kind of debt do you have? Is it this kind of debt or that kind of debt? Like, we're trying to sort all that out before we can figure out how to reduce the debt with our fixed slopes. That better? Okay. The fixed reduces debt. Random just figures out what kind of debt we have. And that's necessary because, like, if you try to put in, like, if you find out that you have only 5% of the variance that's between persons, and you throw in a whole bunch of person-level predictors, the best they can do is 5%. Like, they're not eligible to do other things. So the variance of each kind logically dictates the roles that your predictors have to play and which kind are going to be more helpful.
So would you say we partition the variance
Yes.
rather than control for between persons?
I would say partition, split into piles, decompose is another one, but that sounds sort of morbid. I would not say explain.
Okay.
I would not. And this is something that not everyone agrees with, by the way. There are ways of forming R-squares where people count random things as explained variance, and to me that is just 18 kinds of wrong. Because it's error. Like, no one would argue with you if you said, you know, E is error. Let me find the equation again here. Like, this is either residual or error. Like, no one on earth would say, we've explained it. Look, we have E. No one would say that. But then if you take E and you split U out of it, some people will be like, look, we explained it. Like, well, what caused that person's U? Well, I don't know. That's error. So splitting kinds of error does not make the error go away. I think you're saying it's attributable. Like 80% of what's left is attributable to the fact that some people are higher than others. We don't know why some people are higher than others. We know that they are higher. Cheers. Are we awake yet? I am. Do we need to get up and like do jumping jacks or anything? I have made people do that before. I have. When the energy level gets to the point where we're all like this. If you need to get up and stretch, by all means. Could be worse. I heard some undergraduates walking behind me out of the parking lot today complaining that their class lasted 50 minutes. I wish it were 45. Well, guess what? By the time you say hello to everyone and by the time you close class, it is 45 minutes. Like, I can tell you at least it's not 3 hours. We can say that. I did 3-hour classes one semester. I tried it. Hated it. Absolutely hated it. Even though I teach for 3 hours. It's 2 different classes. That's somehow better. But anywho. Okay, that's better. We're attributing, partitioning, not explaining. Okay. All right, I want to bring it back out, bigger picture for a second here, and ask you one last series of questions, and then that may be a place to stop. We'll see. We'll see how long I can milk this for. How's that? Just kidding. I try not to drag things out unnecessarily unless I don't have the next week's lectures prepped, in which case I totally will do that. But if you've checked the web page, I have next week's ready and the following week's ready too. So you can look at those whenever you see fit. Now let's look at this from an analysis of variance sort of lens. And I think you're going to like this answer, Ahmed, trying to get C out of there, because you asked me about fixed versus random. Yeah, and I showed you this. You may not remember, but I remember. It's like, that was last week. Come on, that was 1,000,000 years ago.
Oh, yeah.
Yeah. So this is our model. If we look at this with our factorial ANOVA like experimental design hat on, you can picture this as like a 3-way box where you would have like maybe people as rows, and then columns might be groups, and then occasions might be the third dimension that's going this way. So if I have 3 different sampling, not only sampling, let's go with design dimensions. What do we call those? Somebody give me a word. What does Ariel call them? The dimensions of the ways, like 3-way factorial. Okay, variable. All right, no one's going to play along with me. Fine. 3 variables. So if I have a 3-way design like this, 3 factors, maybe that's what they call it. Factors means something else in the rest of our classes, though, so I don't want to do that. We have time as a main effect, potentially. Treatment as a main effect. We have people as a main effect. We would have 3 different 2-way interactions and 1 3-way interaction. Like logically possible. Those are all the things that we could have. Now let's figure out what we have and what we don't have. Do we have a main effect of time represented in our model? And this is not meant to be a trick. Where is it? B1. Yeah, beta 1. There it is. Do I have a main effect of treatment? Yes, I do. Do I have a main effect of person? That face, that's where I'm going. That meme, right? Do I have a main effective person? Doesn't look like it if I look at the red parts, like there's no person thing here. What about the blue parts? Yeah? Nodding? Do I have a main effective person, Erica? Yeah, which one is it? Yeah, that's right here. U0, that's my main effective person. That's what it is. It's a random effect, not a fixed effect. Random means I'm estimating a variance across people rather than saying, here's your mean for person 1, here's your mean for person 2, here's your mean for person 3. A fixed effects version of a main effective person would be, I've got, 50 people here? That'd be 49 dummy codes. And then I would have a main effective person across those 49 because they would perfectly recreate all the row means in my data. if you were to output these U's, you could get back to that. Like, you can do that in software. It's not a great idea because they're shrunken, but you can do that. So this is a main effective person. Conceptually, that is what U is doing. It's controlling for which person is which and giving average differences as a function of that. The reason that we're doing it as a random effect and rather than a fixed effect is so that we can predict it. Like, why is person 49 doing so much better? Oh, because they're 49. You know how 49 is. Like, that doesn't help me. Like, I can't take that and like go to a different sample and have it mean anything. And I can't ask why treatment and control differ from each other if I've got 49 dummy codes in because they already did it all. It's saturated. So random effects allow differences still, but differences that are explainable. Debt that can be reduced with your fixed slopes. Okay, with me so far? Let's do two-way interactions. Do I have time by treatment? Yes, I do. Right here. Do I have person by treatment? Could I have it if each person is in only one group or the other? Is person by treatment a thing I could get? No, because that would imply I want to see like how people differ when they're in the treatment group versus the control. I can't know that. They're only in one group or the other. And if I can't have person by treatment, then I can't have the three-way that goes with it, person by treatment by time. That's not going to work. I would have to have what is known as a like doubly repeated design where each person is in each group at each occasion. Then I could do that, but I don't have that. If I put each person in each group, then I'd have to worry about carryover effects and that kind of thing too. So they'd have to learn how to be untreated, which doesn't happen, hopefully. So that leaves one that I'm missing. Which one did I skip? Person by time. Is it in there or not? It's not time, it's E. That's what E is. That's all that's left. E is why did people change differently than they were predicted to based on their group and how everyone else changed. That's E. That is another alternative explanation of what E means. It's not error, it's individual differences in change, duh. Perfectly measured. That should feel uncomfortable to say, because it should be. I have a picture for this. I have a ginormous R matrix. That's not what I wanted. I wanted this picture, slide 16. Here's two different versions of the same reality if you have two occasions, and why I had said last week that two is not enough. Either, let's say that these orange and purple people are from the same group, okay? Either everybody gets a different mean, which translates into a different starting point or ending point or mean because all these lines are parallel within a group, and there's some error around the mean for each person given by E, or I give each person their own rate of change, and if I only have 2 points for each person, that line that I give them fits perfectly. Has to. So either I have an extra type of U that is individual differences in change, or I have an E, but I can't have both. How do I fix it? More data. Yep, 3. 3 is what you need. Request to say this again. Yes. So on the left is a version of reality in which each person needs their own mean, but they have the same rate of change, and there's just some error around that rate of change. Or each person needs a different slope, and because they only have 2 data points that slope is connecting, the slope fits perfectly and there is no more error. It is the same information either way. It's just the interpretation differs. So to have both at the same time, to have individual differences in change and have that line not fit perfectly, you need a 3rd dot in here somewhere so that this line has room to be wrong. Then you have error and the potential for individual differences in linear change. But if you want to have individual differences in nonlinear change, you need 4 or more. So it scales up. More is better. 2 is not enough. All right, did that help, Zoomers? Yes. Okay, cool. So I make this connection not just from a design point of view, but also so that you smell bullshit when you read it in the world of structural equation modeling. Yeah, that's a technical term. So there are models that have been put forth by otherwise perhaps well-intended people, latent difference scores, where they put a triangle in the model that's supposed to capture a latent difference between 2 occasions, and that triangle somehow magically has variance to it. They have to shut off one of the residual variances of the boxes underneath to make that identified. So whether you have 2 boxes that each have variance with some covariance, or you have 1 box and 1 triangle, 6 and 1/2 dozen of the other. So there's nothing magical about switching to an SEM framework that gets you around this fundamental design limitation. You only have 2 variances and 1 covariance. You can't split that into more than what it is. So I think it's a lot more reasonable to say the scenario on the left is plausible than the scenario on the right. If you only have 2 occasions, there's probably nothing wrong with taking the change between the 2 and treating that as an outcome. Like, I've seen people do that, change score analysis. It's not great, but it's the best you can do with 2 occasions. You're stuck. All right, that is where I wanted to leave things. Yeah, not today. I want to do this day. Yeah, one more slide, then we'll go. How's that? It goes with the topic. So more about fixed versus random, slide 17. So this is the part that I usually hide from folks. I talk about time is nested in person. That's a shorthand. That's not technically true. If your data are balanced, where everyone has the same possible occasions, time and person are crossed. The way that you would think about it is each observation is nested in people, each observation is nested within an occasion, and the people in the occasions are crossed. Like, think of a 2-way table. That means we have the opportunity for person mean differences, time mean differences, and then remaining within person by time differences. This is like a G-theory perspective. For those of you who've had that, that's where I'm going with this. The reason that we can say that they are not crossed anymore is because once we control for, and I mean that in the fixed slopes kind of way, once we control for why some occasions have different means, why we put a slope in or let them just have different means, that crossed second dimension goes away. So what's left is just person and person by time as the residual level 1. So time within person is a shorthand way of saying person by time nested in person, because time is going to be taken care of by fixed slopes instead. Now that is appropriate when you have a limited number of occasions and you can have a pretty good sense as to what the trajectory should be. That allows you to add random slopes where people can get individual differences and change. An alternative, though, is to keep time as a random factor. So here's an example of a study that did that. They were looking at reliability in item level data, where each person answered each question every day. And so they have variance across people, variance across occasions, variance across items. Then they have person by occasion, person by item by occasion is the residual. You can do it that way if you want to. But then you are, you're treating differences across occasions as random. Like, well, I don't know why this occasion is different. It just is. As opposed to, I'm going to put in a slope that says, no, I'm going to say that occasion 2 is higher than occasion 1 and occasion 3 is higher than occasion 2. So it's up to you. It's contextual and it's based on the design of the study. Time is not always level 1. That's also the case, right, Vladimir? Yeah, so he's helping with the project where it is a state-level survey over time, but each time they asked the questions, it was to a different group of respondents. So people are nested within their survey year. Survey years are nested in states. Time is level 2. So in his design, he actually has a crossing of time that he will have to deal with in that context. Time can be level 3. I had a student once from Survey Research Methods in University of Nebraska who had respondents to a survey nested in who asked them the questions, the interviewers, and then they had that for 1 year of data. The next year, they went and got all new interviewers and all new respondents, and they kept doing that. Time is level 3 in that case. And so he came to the longitudinal class, and I was like, dude, this isn't longitudinal data. Nothing has been repeatedly measured. You just have a bunch of years of data stacked together. So if something changes, you have no idea why. So time is not always level 1. It depends on the design. But we are going to be controlling for differences across time so it doesn't need to be another crossed random factor. That's the longer explanation. And now you're like, yeah, you should have just lied to me and told me the time is nested in person. But I don't want to lie anymore. All right, there, 142, I did it.
I have one question on
Yeah.
that. So if you have participants where you have, if you're like looking at continuous age, basically an accelerated longitudinal design where you have different, someone might be 3 months, 6 months, 10 months, and then another person's a year, 18 months, 24 months, something like that, then would time need to be random in that instance because it's not necessarily everyone having all instances?
Yeah, so the question was about accelerated designs where people start at different points in time and then they have different distances between them, so everything's all uneven and unbalanced. In that case, I think it would be very difficult to estimate a crossed model because you need at least enough commonness to get like what it would be for this particular occasion. You'd have to have more than one person at it to get a commonality. In that case, it might be more reasonable to start from time as nested in person because we don't even have a common schedule by which to estimate common means. Right. Other questions? Comments?
I have a question regarding the interpretation of the interaction too, you mentioned,
Yes.
more or less, and that
This one or the
yeah,
E thing?
Yeah. So if we have, for example,
No. Where do you want me?
No, the other one.
The other one.
The example. Yeah.
Yeah, the
So, for
equation.
example,
Should have
yeah.
guessed.
So back to this table, if we have the time was negative 5.8, for example, and the time interacted with treatment is negative 2, so this considered like less negative or more negative?
If the time effect was negative and the
Yeah,
interaction was negative,
yeah.
that's a more negative.
Regardless of the values?
Which way is it going relative to 0 would be my question. So if the control group
Closer to
changes
0.
negative 5 and the negative interaction means that the treatment group would change negative 7, that is a stronger slope.
Yeah.
So more negative to me means like a stronger negative decline, I guess is the
Yep.
word you would use
Yeah.
in this case. Yep.
Okay, thank you.
Yep. All right, others. All right, then it's Thursday. That means have a good weekend. Let me know if you need anything. Try out Homework 0. Bye for now. Thanks for being here. Bye, Zoomers.